Time for remarks. The first remark is about this additional condition here, that not only an be convergent to A, but also the adjoints converge to the adjoint. Is that really an additional condition? In the sense that does it not automatically follow from an to A, which we impose anyway? And the answer is yes, it is an additional condition. And here is an example. Let an refer to the operator on little l2 that is given by the following infinite matrix. You place a single one entry in the first row, nth column. So it's the top right corner of this n by n finite section, and all the rest is 0. So as an operator, this takes an infinite vector from L2 and maps it into the infinite vector that has xn in the top component, and all the rest is 0. Now clearly, because your input vector is an L2, its entries form a null sequence. So this entry xn must go to 0 as n goes to infinity. So this whole vector here goes to the 0 vector as n goes to infinity. Of course, you can write the 0 vector as the 0 operator applied to your input vector, or in other words, an converges to the 0 operator strongly. So we have an example where an converges strongly to some limit a, and in order to show that not automatically an star converges to a star, we should check what an star is doing as n goes to infinity. So fortunately we are looking at Hilbert spaces here and here, so we can form the adjoint. And we know that the adjoint operator is simply given by the adjoint of this matrix here. Now this maps an input vector into the infinite vector that has x1 in the nth position and zeros everywhere else. Now as n goes to infinity, this entry x1, which is possibly a large number coming from the first entry of this arbitrary L2 sequence, is not changing. The only thing it's doing is moving down the vector. But the sequence of vectors that you get in this way is not convergent. It's not a Cauchy sequence in L2. The distance between two arbitrary such vectors doesn't go to 0. So this sequence does not converge. And hence the operator sequence an star does not converge strongly. In particular, it does not converge to the adjoint of this limit here. Okay, that was remark 1. Our second remark is about the interesting connection that theorem point A is giving us between stability, invertibility of A, and applicability of the sequence. From the old Polski theorem, we are used to the equivalence arrows sitting here and the AND word sitting here. So what's this change all about, and what does it mean if you put the two theorems, old and new Polski, together? So it's all about these three properties, and the old Polski theorem says that applicability implies both invertibility and stability, and that invertibility and stability, if both of them come together, then they imply applicability. Now, statement A of the new Polski theorem moreover says that stability on its own already implies applicability and invertibility, and that applicability and invertibility together imply stability, but that's already clear by this arrow here. Already applicability on its own can do that. So if we entangle or simplify this network here, this graph, we find that applicability and stability imply each other, so they must be equivalent. And each of them implies invertibility, but not vice versa. And the roles of these three properties are still pretty clear. We want applicability of our method. And in order to get applicability, we definitely need stability. Okay, we know this from the old Polski theorem. But in the old Polski theorem, we also used to say that we guarantee invertibility of A. And then this, together with stability, implies applicability. But this is no longer the case. So due to new Polski and due to the additional condition that also the adjoints converge strongly to the adjoint, we get invertibility for free as soon as we have stability. Now stability on its own is the key. We don't need invertibility anymore. We don't need to make sure the operator is invertible. If we have stability, then we get that automatically. Okay, so invertibility of A is no longer an additional condition that is independent of stability. No, it is part of stability. It follows from stability. So of course we also need it, because if it's not the case, if your operator is not invertible, then the sequence couldn't be stable. But as soon as we have stability, we don't have to worry about invertibility anymore. That's the message here. Okay. And then a third remark. In the theorem, we say it even twice, that the Moore-Penrose pseudo-inverse of A exists. And we never worried about that fact before. We always thought that it always exists, it automatically exists. So why even talk about its existence? Well, maybe it's not automatic. Okay, so third remark. The Moore-Penrose pseudo-inverse exists if and only if, what goes here? Let's try and remember how we define or how we characterize the Moore-Penrose pseudo-inverse. Remember that it starts by an orthogonal projection of your right-hand side down to the image of A. Then you follow your operator backwards to a particular solution for that new right-hand side here. Maybe here. And from there you project again orthogonally onto the orthogonal complement of the kernel, and that gives you the little x. And your Moore-Penrose pseudo-inverse is just what you get when you combine these three maps one after the other. So what can go wrong here? How could this whole construction break down? Well, it could actually break down in the very first step. It could break down when you want to project your B down to your image of A by an orthogonal projection, because that orthogonal projection here doesn't exist when the image of A is not closed. To say it short, the image of a projection is always closed because it's always the kernel of the complementary projection, and kernels are always closed. So if it's not closed, then it's not the image of a projection, and that's where things can break down. And actually that's the only point where things can break down. So your Moore-Penrose pseudo-inverse exists if and only if the image of A is closed. Actually, you could also argue via best approximations. So this orthogonal projection here, this blue element, is supposed to be the best approximation of your right-hand side B inside the image of A. But if the image of A is not closed, then B could be part of the closure of A without being in the image of A. But then if it's in the closure, then its distance to the image of A is 0, because it can be approximated as good as possible with distance 0 by elements from the image of A. But then what is its best approximation? I mean, it doesn't get better than 0, but that would be B itself, and that's not in the image. So you get problems if your subspace is not closed. Okay. Well, fortunately, if A is just a finite matrix, then the image of A is a subspace of the m-dimensional vector space. And in finite dimensions, every subspace is closed, so that the pseudo-inverse always exists. So indeed, we didn't have to worry about the existence of the pseudo-inverse so far, because we've been only looking at finite matrices. But our theorem is for operators for infinite matrices, and there this question is not trivial.